Hello everyone, Grzegorz Baron here. In this video I'm going to present a full photogrammetry workflow for material scanning, but this time with the main focus on 3D Zephyr used for photogrammetry reconstruction. As a subject of reconstruction, I picked an old brick wall. In details, I'm going to present the capture part with the monopod used to follow surface verticality, raw image pre-processing and the lighting pass with the Photolab 3, a photogrammetry reconstruction with the 3D Zephyr. I'm going to use ZBrush to build a low poly model for texture baking. I'm gonna use the Substance Designer Baker to bake set of PBR textures. Due to a tricky pattern type, I'm going to remove edge seams and tile the textures manually with the Substance Painter's clone tool. And finally, I'm going to generate a missing roughness map and test the final material in Substance Designer. In result, we should get a high quality, ready to use in any 3D engine PBR material of brick wall. As always, bear in mind that this is just an optional workflow and there is no the only one or just the best one tool to do the job. Each has its own pros and cons and each is in constant change. This is why I strongly encourage you to play with them all and pick the one which suits you the best. I hope someone finds something useful in here and let's begin. I have found a really interesting spot full of industrial materials next to the South Shields dockyard. For this exact capture I decided to pick a quite old but still clean brick wall. The capture took place during pretty cloudy day, but since there are still gaps in the clouds, I picked the part of the wall hidden in its own shadow. This way I was sure I can avoid any unnecessary direct shadow and lighting inconsistency I would need to deal with later. Since I wanted to reconstruct exact 180 by 180 cm large area, I put two rulers next to the wall, both unfolded to 180 cm, one on the ground and one leaning vertically against the wall. This way I mark the area to capture, so it's easier and more efficient to navigate with the camera, but also got the additional scale reference embedded into the reconstructed scene. I found it very useful to define size of the low poly model later. Next, I took a few pictures with my mobile to document the wall. I do it usually in case I need more context information while setting up materials details like the height or roughness. This is why I captured my shoe, as it gives additional context for the real size and height of the surface. Next I set up the camera. I set the ISO to 100, the aperture to 8, which should be totally enough for this type of capture, set the custom white balance and capture the X-Rite color checker as a color reference. I set quite wide 24mm focal length as I prioritize the capture of sides height information to details per frame. Also, wider focal length lets more light to get into the camera, so less exposure time is needed to take each photo. With this setting, in these lighting conditions, I managed to get 1 per 60 seconds shutter speed, which is great for this type of camera stabilization, especially that I was planning to shoot from the really close distance. Because the vertical ruler was wobbling due to quite strong wind, I decided to fold it back and proceed just with the bottom one. Since I wanted to take series of consistent and perpendicular to the brick's wall surface images, I mounted the camera on the monopod and extended it to its full length, so I can move it around and keep the same angle and distance to the wall. With this type of capture, a remote shutter release is a must and I used a cable one. I wired it around the monopod so it doesn't rattle too much and I started the capture. The full capture took me 8 minutes. During this time the sun came out for a while, but since the wall was hidden in its own shadow, it didn't affect the capture. Since the monopod has a minimum height, I needed to handhold the camera to capture the bottom part of the wall. It wasn't a big risk since I planned to use the bottom part of the capture only as a scale reference, as it included the ruler. To secure additional data for image alignment, I took 2 more images, which frame entire wall from increased distance. Also, I can use them to create a PBR material with the Alchemist and its AI-based image to PBR technique and compare the result with the photogrammetry based one. Anyway, the capture was over and it was the time to process the data. As you can see, all 164 images seem to be sharp and consistent, but they still need to be tweaked a bit. Please keep in mind that while we work on raw files, any changes done at this stage are considered as lossless, especially when compared to what we get if we work on 8-bit data carried by JPGs. This is why I strongly recommend to shot RAW to JPG when possible. The first thing I did during the RAW post-processing pass was to make sure that the white balance is set up correctly. I simply set the white balance again using neutral middle gray clip of the captured color checker. Next, since even without the direct sun there are still shadows casted by the sky, I played with the blacks, shadows and highlights in selective tone setting to calm them down and delight the images. I have learned to be very careful with this setting as it might affect the color and push it into totally unwanted, unrealistic direction. It's worth to observe how these changes affect the color checker. We can preview the difference before and after the changes were applied to make sure we didn't do anything crazy with our tweaks. Let's bring a bit of contrast, as this way we can get even more surface micro details for reconstruction. Bear in mind that for photogrammetry we should turn any lens distortion fixes off. The main reason for this is that the photogrammetry software is going to make this job way better. I think that's it for this capture, and we can export all images as 16-bit TIFF files. Storing data as 16 bits can be really beneficial for image alignment with the photogrammetry software. When done, we can proceed with the 3D photogrammetry reconstruction. Let's open the 3D Zephyr and start a new project to load all images we want to use for reconstruction. As you can see, the 3D Zephyr is based on a wizard system to make the process more user-friendly. Let's keep the suggested setting and hit Next to move to the next step. Next, let's load all the images except the one with the color checker included, as it wasn't used as part of the capture. When done, the software has to estimate camera positions in 3D space for each image. We need to help 3D Zephyr a bit by picking correct alignment setting. To communicate with the software, 3D Zephyr offers a project wizard which usually contains 3 main modes: a basic one, an advanced one and a custom one. The basic one is based on a preset system where we choose very basic setting to proceed with. The second one is based on detailed preset system and gives us more options to pick from. As you can see, when we hover mouse over the setting, we get the helpful description at the bottom telling us what each setting does. But if for some reason something goes wrong and none of this works for us, we can always use the third, custom one, and set the advanced setting we need. In this case, the software also offers help so we can read what each setting does. For example, I use this mode when I struggle to align cameras in quite tricky 3D capture, and to do this I increased the numbers of features to 600 and maximum tracks per camera to 100. Just bear in mind that if we go back to a preset system, it will reset all changes we made. As you can see, the value I changed is set back to what it was. Okay, let's use the preset system to align images. When we are happy with our choice, let's hit the Run button to start the image alignment process. During the process, 3D Zephyr offers some live preview so we can see what resources are being used and a bit more details of what actually happens. As you can see, all images were aligned. We can see all close shots and 2 additional taken from a distance. In cases when we missed alignment for some, we can reorient them manually by hitting the right mouse button on them and proceed with similar procedure. The only difference is that during this procedure we would need to select images which share some space with those non-aligned. Let's save the project now and proceed with actual photogrammetry reconstruction. To proceed with the reconstruction, we start another wizard. Same as before, we have 3 setting options: preset, advanced and a custom one. This time let's go with the advanced one. Same as before, we just need to hover mouse over the option to get more details of what each does. Since I aim to get highest possible quality and reconstruction time doesn't matter, let's set the number of nearest cameras to 5, resolution to 75%, speed up level low, hyperplane matching on, cameras preselection off, and update colors on. It's good to understand that 3D Zephyr has two main reconstruction passes, which can be processed separately. The first one, called Stereo, is a simple 3D photogrammetry reconstruction which results with a generic 3D mesh. To bring medium and small details, we need to apply the second one, a photo consistency pass. As I mentioned, this pass can be applied during the main reconstruction, but can be also applied later as a filter, and this is what we are going to do. This way we get a bit less destructive photogrammetry workflow, as we don't have to start from the beginning if we are not happy with the final result. There is no limit to amount of photo consistency passes we want to apply, and we can mix them together. Of course, it takes time to process each. And this is the result. It took 2 hours and 20 minutes to generate this mesh on my computer. It has 7.5 million triangles. As you can see, it lacks of medium and high frequency details, but we can bring them by applying a photo consistency filter to this mesh. We do this by hitting the right mouse button on a mesh in project space and selecting filters from the context menu and photo consistency based optimization. This way we open another wizard with advanced and custom sub-windows. Let's set the image resolution to 100%, hierarchical subdivision to 2, reprojection area to 5, high frequencies gain to 0.01, enhance filter to 0.02, the edge filter to 0.01. and apply the filter. At this stage we can decide if we want to apply filter to already existing mesh and override it, or do we want to apply it to its clone. The second option makes more sense, as this way we can always go back and save 2.5 hours of initial reconstruction when we are not happy with the photo consistency pass result and want to repeat it. And here is the result. This single photo consistency pass took 1 hour to process and increased the mesh density to 37 million triangles. There is no simple rule how to set photo consistency values, as it depends on the certain capture and image quality. To understand the setting and how it works, I simply processed a few photo consistency passes with different setting and compared the results. Each took about 1 hour to process. And here they are. All were applied to the initial mesh, so I can clearly see how exactly each setting affects the result. Overall, I found photo consistency a bit tricky, as the result is based on combination of all these settings together, as each settings affects others. Anyway, this is the setting I decided to use for this brick wall. Since the brick wall color we see on the screen is based on vertices only, let's generate a texture and use it to carry albedo for baking. This way we get independent to mesh density source of albedo. It can be especially useful when we plan to generate very high resolution textures. Let's hit the textured mesh generation button to open texture generation wizard. Select the mesh we want the texture to be applied to, and since I took 2 images from the distance, let's exclude them from the reconstruction. Let's set the texture's resolution to 16K to make sure we have enough albedo data when baking from it. Because texturing in 3D Zephyr automatically splits textures per 10 million triangles chunks, we might get more than just one texture. It was made to help with texture generation on computers with lack of memory. To avoid this, we need to go to custom options and increase the max triangle per cluster value from 10 million to something higher. Since our mesh has 37 million triangles, setting it to 40 million should be enough. When done, we can hit the run button. Texture generation for large meshes can take a while, and in this case it took 23 minutes. When done, we can find the textured mesh in Textures Meshes section. Now we can export our high poly mesh. And the texture. To build a low poly model, we can also export additional smaller supportive mesh and bring it into the ZBrush instead of a very heavy high poly version. This way ZBrush is going to be much more responsive to navigate. I did it by exporting our initial 7 million triangles heavy mesh 1. Now we are ready to create a low poly model, which is going to be used as a canvas to bake high poly data from the high poly model into the 2D texture. To make it happen, the low poly model we are going to create has to align with the high poly model in 3D space. So let's bring our 7 million poly dense one to ZBrush. Next, let's bring a 3D plane we are going to use as a low poly model. Next, let's apply any texture with readable directions so we can see UV mapping direction. Basically, where is the top and where is the bottom of the texture. UVs at ZBrush are flipped, so in practice the texture which is flipped upside down is correct. So this is the mapping we need. Now we can remove the temporary texture. Next, we need to scale the plane to match our ruler, as we know that the ruler marks the area we want to turn into a texture. When done, we need to align the plane with the high poly model. To make tiling easier, the top and the bottom edge should match the gap between brick rows. Next, we should decrease the plane density a bit, so it won't fall into gaps when we align it with the projection tool. Let's project plane over a high poly version. This way we shouldn't get a cross-surface gradient on a height map later. I'm not happy with a few spots, but we can fix them manually using the Move brush. Now let's align top at the bottom edge manually with the gap between bricks. Okay, I think we are done here and we can export the plane 3D as a low poly model. Now we can bake all the data with the baker. Let's use Substance Designer Baker. Let's set up a new project and bring our low poly model, which is going to be used as a baking canvas, and set up the baker. Since I decided to use a texture to carry color information, we need to select the one exported from 3D Zephyr as a source for albedo information. When done, we should have them stored in our baked directory. Since they don't tile at all and have visible seams on every edge, in the next step we need to remove those seams. We can try to make it automatically and sacrifice some material quality, or we can do it manually brick by brick, and this is what I'm going to do in Substance Painter. Let's start a new project and bring a 3D plane I'm gonna use to remove all seams. This plane has a special UV mapping, so it's going to be easier to work on textures edges. Next, let's remove existing layer and create a new fill layer. Next, let's activate channels matching our baked set of textures. Next, we need to bring our maps and assign them to proper channels. Next, let's offset textures to get seams cutting the plane in the middle. This way we get a better visibility of what we are doing. To activate the clone tool, we need to add paint. and set all its channels to pass through. This way we can activate our clone tool and use it. By pressing V, we select the area to copy from. We can switch to full window mode by hitting Tab. By hitting it again, we bring full interface back. By hitting C, we can preview each channel separately. By hitting M, we go back to full material preview. Now we need to solve the puzzle and copy and paint bricks to cover the seam area so they look natural. I suggest to move light around from time to time to make sure everything works fine. When we are happy with the result, we can export final textures. The last thing left to do is to generate a roughness map and preview the final result. To do this, let's bring all textures to Substance Designer. The best and the easiest way to do this is to use a color map. Since in roughness everything what is dark is shiny and polished and everything what is white is rough and non-reflective, we should invert it. To get a bit more control over the result, we can bring levels node at the end. To get more consistency across the roughness map, let's process a high pass on it. Since usually areas in shadow shouldn't be reflective, let's multiply the result with the ambient occlusion map. Since a brick wall isn't reflective at all when it isn't wet, let's tweak the output value with the level node we added before until we are happy with the result. And let's export the final texture. And this is the final texture set of the brick wall material, which can be applied to any surface in any PBR rendering system. And I guess that's it for this video. I really hope you enjoyed it and found something useful in here. If you like it and want me to create even more content like this one, please leave the thumbs up, drop a comment and subscribe to my channel. It really helps me to move forward with my research and to share all the results with you. Big thanks to all of you who did it already, and hopefully see you next time. Stay safe and bye!